Hi, I'm Phil, and I'm presenting our work, Evidential Softmax for Sparse Multimodal Distributions in Deep Generative Models. Deep generative models with discrete probability spaces encourage distributional multimodality and thus have had success in multimodal tasks such as image generation and language modeling, where there are multiple valid possibilities for the output. However, prohibitively large discrete probability spaces are required to accurately learn complex data distributions, thereby causing difficulties in interpretability and rendering downstream tasks computationally challenging. For instance, robotic motion planning algorithms often plan using a uniform distribution over the entire state space representation, requiring exorbitantly many samples to accurately cover a large latency space. Therefore, we investigate whether we can improve discrete generative models by predicting sparse probability distributions, which would enable efficient marginalization over the probability spaces, even if these spaces are very high dimensional. One approach to a sparse normalization function was introduced by Itkina et al., who proposed a post hoc procedure to sparsify the latent space of conditional variational autoencoders at test time. Their method was able to sparsify latent distributions of CVAEs using evidential theory to interpret input feature vectors as evidence. Conflicting evidence was associated with multimodality, and a lack of evidence was associated with sparsity. We introduced Evidential Softmax, or Ev-Softmax, a generalization of the post hoc method introduced in Itkina et al. To training time. Ev-Softmax is compatible with the negative log likelihood and KL divergence. Our paper also investigates some properties of Ev-Softmax and its continuous approximation, which we use for training. We found that our approach was able to outperform baselines in distributional accuracy across image generation and machine translation tasks. In this paper, we found a simple closed form for our post hoc sparsification procedure. Here, it is presented next to Softmax to demonstrate the parallels. Ev-Softmax takes as input the output of the last linear layer of the network. It requires O of k computations. The sparsification happens according to a very simple condition. If the logit output Vk for class k is greater than the arithmetic mean of the logits over the classes, then that probability mass is kept. Otherwise, it is pruned. We derived the Jacobian of Ev-Softmax and found that it holds distinct parallels with the Softmax function. We would hope then that the training behavior of Ev-Softmax would be fairly similar to that of Softmax. In order to train with this sparse distribution, we use the training time approximation by adding epsilon to the indicator function here. In the limit as epsilon goes to 0, the negative log likelihood term takes a similar form as that of Softmax. We first evaluate this method on our toy example with even and odd digit generation. We use the same CVAE architecture as before in the Itkina et al. Paper, but now we train with the respective distributions, Softmax in yellow, Sparse-Max in orange, Entmax 1.5 in blue, and our Ev-Softmax in green. We found our distribution in Softmax to produce the most reasonable looking latent spaces. Sparse-Max and Entmax 1.5 would often collapse the latent space. Our distribution over the latent space seems to overall be the most reasonable. We again test our method on the large-scale VQVAE network, this time training on tiny ImageNet with 16 by 16 latent variables with 512 latent classes. Here, k is the average number of latent classes kept by each distribution, and we consider top 5 and top 10 accuracy. For this experiment, our method is less sparse than Sparse-Max, but more sparse than Entmax 1.5, while achieving the highest accuracy. Thus, for this task, correctly balancing multimodality and sparsity appears to be important. Lastly, we also tested our method as part of a transformer architecture for machine translation to achieve sparse self-attention. The idea here is that the attention mechanism should want to pay attention to multiple words in the input sequence, but potentially not all the words at once to avoid wasting probability mass on irrelevant source words. We see that our method achieves the highest scores across all the metrics on these models, while attending to a larger number of words than Sparse-Max and Entmax 1.5. In conclusion, we have presented a sparse normalization function grounded in evidential theory for use in generative models with categorical output distributions. All our code is publicly available at these links. Thank you.